Hello, hello, test, test. Ladies and gentlemen, this event will start within 1 minute. But before I start, please let me know if you can hear my voice loud and clear. Say hi or say yes to me in the chat box right now. Thank you. Thank you, Ashwini. Thank you. Thank you, Hazel. Thank you, Ye. Thank you. Okay, now we can start. One more thing I will remind you later. You on your screen right now, you can see there's a blue bar and a red button download, right? You can feel free to download our digital folder to read it now or later after the event, so you can get to know this event better. This downloading button, I will keep it open until our first speaker. So for my opening speech, you can still have a time to download our digital folder today. So let's begin. Good afternoon, ladies and gentlemen. I haven't formally introduced myself to you. Thanks for joining us today. I'm Jack, editor for Ringer Events in Taiwan, and your host for this event today. I'd like to welcome you all to our webinar today, titled Additive Manufacturing on Product Sustainability, organized by Ringer Events. In this webinar, you will discover how additive manufacturing can shift your product manufacturing technique seamlessly. This is our first webinar series on 3D printing in our Asian Metal and Plastic Materials session this year. First, let me acknowledge our association supporter, the Philippine Die and Mold Association, or PDMA. You can see it on the screen. To our esteemed industry experts and guest speakers, Dr. Rigoberto Advincula as our first speaker, Ms. Lim Wei-Yen, and also Mr. Jonathan Kao. And of course, to our delegates, thank you for gracing our event today. Additive manufacturing is one of the most promising manufacturing technologies in the fourth industry revolution, or Industry 4.0. The revolution of this industry affirmed that we are at a turning point, where additive manufacturing appears to be the most viable alternative to traditional manufacturing techniques. This technology, joined by artificial intelligence and Internet of Things, IoT, significantly transformed the healthcare sector, enabling major innovation in medical technology, surgical procedure as surgery, right? Such as therapeutics, dentistry, and cardiology, and etc. In Asia Pacific alone, the growth forecast for 3D printing is at 21.4% over the 2020 to 2030 period, with the market cap of $58.83 billion despite the COVID-19 impact. The APAC region is projected to witness the highest growth over the forecast period of 2020 in 2030 as well. This rapid adoption of additive manufacturing in APAC can be attributed to the development and also the acceptance of this process in these industries, especially in aerospace, automotive, and also medical, among the others. So stay with us until the end. We will share from our special experts as well. Yes, we will share many insight points to all of you today. So enough of my talking, and let's begin with our presentation. First on our agenda is the keynote speech by the professor at the Department of Macromolecular Science and Engineering, Case Western Reserve University, and also UKT. After this technical presentation from Aberg, and then followed by the other technical presentation from Manly Plastics Incorporation. Now, before we start, yes, one last thing, really last one. I want to remind everyone, not only you can type in the chat box and speak to me and to the other speakers as well. We will be having live Q&A session right after each speaker's presentation. So prepare your question, listen very carefully to their presentation, and they might gonna answer your question in person later, showing the face to face, talk to you. Seize the great chance today to talk to our experts and also learn from them. That's very important. And also, if you want, you can also leave a message here introducing yourself, where you come from, what's your company product, and what are you good in some fields in the industry too. The other point is here to have networking with the others, make friends, and maybe you can meet your potential business partners too. And also on the chat box, on the top right, there's a gear button. If you want to adjust anything, the audio, the other speaking issues, or you want to, even we have a translation function there. You can explore more by clicking the gear button there. And in the center area, if you found my AV pod, my profile picture, my camera box is too annoying, you can use your mouse to drag this video box to wherever you want, or even click the lower right button. There's a dock button. You can fix this camera box to the top right, and will not blocking the center stage and also the speaker's presentation anymore. So let's begin our presentation. I hope you do enjoy our event today, and also ask your questions, learn something today. So now it's very important. Let me introduce our first speaker. And also very important that manufacturers know where additive manufacturing is headed so they can plan ahead. All the way from America, our keynote speaker, Dr. Rigoberto Advincula, is the professor at Case Western Reserve University and University of Tennessee, Knoxville, or UTK. Dr. Advincula is past chair of the Polymer Chemistry Division, as known as ACS, and previous president of the Philippine American Academy of Science and Engineering, as PAASE, and was inducted member of the World Economic Forum Future Council. It's our honor to welcome you today, Dr. Advincula, despite the very great time difference. Let's welcome Advincula. Now I'll make you as presenter as a while ago. You can turn on the microphone and camera and give a speech too. Delegates, seize the great chance to prepare your questions. We will have live Q&A later. Dr. Advincula, can you turn on the microphone and camera now? Okay, let's give him a few time. Okay, great. Because we have a longer connection. So it's very great chance to listen to Professor Dr. Advincula. Dr. Advincula, do you hear my voice?
Yes. So I'll start sharing my screen. And
yes, you have the floor now. I'll disappear right after you share the screen. Okay.
All right.
Can you full screen that too?
Can you see the full screen?
Oh, sorry, no, not this one. We can only see your back end. So please try resharing your screen again, and try this time use sharing the entire desktop. Share the full screen. Yes.
All right. So we'll do that.
And yeah, you can clear out your desktop first and share the
entire screen.
Entire screen, please.
Okay.
By the way, do you have any video or audio to share too?
Not this time.
Okay, then it's great. Please go to the PowerPoint and try full screen this time. Yes, that's great. Okay. Delegates, say hi to Dr. Advincula. You may have the floor now, Doctor.
Okay. Thank you, Jack, for that generous introduction, and of course, for the organizers of this meeting, the Plastics Association and the Rainier Production. So indeed, it is morning time here. So good morning, good afternoon, and good evening if you watch this later at your own convenience. So today I'm going to talk about 3D printing, plastics upcycling, manufacturing, and the sustainability ecosystem. So I'm right now associated with the University of Tennessee and Oak Ridge National Lab, although I still have my laboratory at Case Western Reserve University. And I'll be happy to answer more about my background later, the Q&A. So plastics. We cannot do without plastics today, whether we use it for packaging, for textile, or as additives in paints, formulations, different types of manufacturing for car parts, automotive, aerospace, And indeed, it's put a boon and a bane in that there's a lot of uh, plastics that need to be recycled. Today, we have most of our plastics produced by what we call formative manufacturing. Formative means we can use molding, extrusion, injection molding, blow molding, thermoforming, and this enables the production of plastics in very high volume. And indeed, the tooling, methods of refining the process, as well as high production, is the name of the game. Uh, Polymers are large molecules. They can be based on a linear architecture, branch, hyperbranch architecture, highly cross-linked. Therefore, we have the terms like rubber, plastics, epoxy, or what I would say thermoplastics, thermosets, or elastomers. And therefore, the word polymer is a much bigger term that encompasses not only industry, but also the science. Actually, polymers play a big role in nanotechnology. We specialize, my group in particular, specialize with the nanostructuring of polymers at interfaces, production of membranes, polymer brushes, gels, different types of colloidal particles. And as you can see here, we can get very high aspect ratio as well as particulate types of polymer materials. Now, where do we get petroleum plastics, which are derived mainly from fossil fuels or petroleum? We can see here that as a product of the refining process, together with high distillates or other types of organic materials, we can derive ethylene, propylene, which can also come from natural gas as the base material or monomers for producing plastics, or in this case, polyolefins. Polyolefins include polyethylene, polypropylene, polystyrene or other vinyl polymers. On the other hand, polyesters, nylon, polyurethane, these are plastics or elastomers that can be derived by step polymerization. In the Philippines, they have a production there based on cracking of petroleum or refining, which of course produces not only gasoline, but some base materials in the upstream. On the other hand, a cracker, let's say the one operated by JG Summit, would be responsible, let's say, for producing polyethylene or polypropylene based on homogeneous or even heterogeneous catalysis. And so plastic production is very much tied to the oil and gas industry in the upstream per se, such that when the price of oil is high, the price of plastics is affected. However, it's a problem in that majority of the plastics is not recycled. As you can see, it's a pollutant not only in our rivers, landfill, or for incineration purposes, which is actually good. You can use them for energy. A lot of the plastics end up in the ocean, or plastics that were produced are still around with us today. That is because plastics is based on a linear economy. In fact, you can say about 10% of plastic is ultimately recycled. A good 90% ends up in the linear process, being used in landfill, incineration, ends up in the river or the ocean. It's a big problem, and therefore turning a linear economy into the circular economy is a big goal for both science, engineering, and industry. Circular economy means that you get this feedstock, perhaps based not only on fossil based feedstock, but also bio-based feedstock, recycle, reuse them, upcycle, and therefore little of it ends up in the landfill, or what can be construed as waste or even incinerated. Okay, so the circular economy is the goal, or one of the ultimate goals for improving the plastics economy. In what we call a life cycle analysis or LCA framework, it takes advantage of the ability to account for energy usage, for CO2 emission, and the best framework to achieve very good LCA numbers is to recycle, reuse, and use this in a circular economy, obviously. And this LCA goes for any other type of materials or production process. In fact, if you turn this into a linear scheme where you account for both input and output for production of plastics, then you would look for extraction, transportation, pre-processing, chemical conversion, product transportation or use as part of that process, and minimizing the amount of energy or CO2 emission or reduction in the cost of manufacturing or transport are all part of the game. In 2016, I was fortunate to be a member of the World Economic Forum. They invited me to give a talk on the future of 3D printing, where 3D printing or additive manufacturing will play an important role in industries based on robotics, bio-inspired design, manufacturing, tissue engineering, or inner space, outer space manufacturing. High value adding means that one is able to use this type of manufacturing and use, let's say, recycled materials and improve their properties. And as you'll see later, the 3D printing goes into many, many industries today in terms of future value chain. So, for example, if you just want to start 3D printing, you can buy your own 3D printer based, let's say, on fused deposition modeling or filaments. One can start the project right away with a CAD design or download a file, an STL file. However, manufacturing based on 3D printing can be in the form of rapid printing, such as the carbon print technology, or big build volume in terms of big printers, including the big area additive machines, or other types of FDM methods. Where 3D printing shines is where you have design complexity and high performance. The complexity of design necessitates that the additive manufacturing can have advantages in both material and design over other types of formative manufacturing, or that is based on casting or molding. So where 3D printing shines, it falls short in the production goal. There is a manufacturing gap between additive manufacturing and formative manufacturing. Formative, of course, refers to molding, extrusion methods where one can easily reach a million prints or a million shots of the object, whereas in additive manufacturing, you're limited or uh, are limited, let's say, to 1,000 to 10,000 pieces until you have to reload, or you can go towards what we call massive or farm printing. Another type of manufacturing based on subtractive manufacturing actually competes with additive manufacturing, except that additive manufacturing has advantages in terms of less waste of material. Okay. So milling, cutting, things like this are called or part of what we call subtractive manufacturing methods. Now, with additive manufacturing, you have a number of techniques. So to demystify the abbreviations, FDM refers to fused deposition modeling. SLA to photopolymerization stereolithography. Selective laser sintering is basically vat powder printing. And I'm not even talking about methods associated with metal 3D printing or ceramic 3D printing. And there's yet about 10 or even 15 types of printing methods that are available. And some of them have been making inroads in commercial printing. Now, talking about plastics, I mentioned about polyolefins. A lot of that constitutes what we call commodity plastics. However, in this pyramidal scheme, uh, not the Ponzi scheme, you have performance versus cost uh, valuation. The higher you go to the pyramid, the higher the performance, such as peak PIC, or we call this high performance polymers. They can, in fact, replace metals in many cases, but they're very expensive, higher melting point, and perhaps harder to 3D print. But you have a range of thermoplastics as well as thermoset materials and elastomers available for manufacturing. So 3D printing again excels when we look at complexity of design, one of a kind, on-demand production, no transportation if you have the printer on the field, no subtractive manufacturing or waste material generated. So this applies to many sectors. First, biomedical applications. So in the dental, biomedical prosthesis, orthesis devices, or orthopedics, one can use 3D printing to personalize medicine, bioprinting of cells, stem cells. Let's say in the case of bone replacement, you can just change the infill design and volume, and you can change the load capacity or the strength to weight ratio. Another aspect of 3D printing goes to the automotive industry, aerospace. For example, one of the first 3D printed cars was done here at Oak Ridge National Lab. This is an old design that was, in fact, regenerated or reproduced. The Cobra car design was popular in the 60s, but yet 3D printing allowed one to be produced today. So it can go, for example, into parts manufacturing, metal replacement, engine parts, or prototyping of cars, which can be done by 3D printing. So in the automotive industry, strength to weight ratio is very important. And the competing technology, let's say, will be the use of fiber composite, carbon fiber composites. On the other hand, 3D printing can actually be used in the automotive industry if one looks at the molds or the tools or the jigs or the tools that are used for, let's say, um, uh, making metal sheets or forming metal sheets by, let's say, forming or other parts by thermoforming. So I'll explain later where 3D printing can have cost savings in terms of the manufacturing process, primarily by emphasizing on the tooling and molds used for manufacturing. But as you can see here, high strength to weight ratio is very important. In the area of manufacturing, 3D printing of houses, building implements, or hybrid printing has been done and demonstrated with cement, plasticized cement, or perhaps in the future, 3D printing the future moon base using moon dust. Now, the story here is that many applications are yet to come and are being realized, whether it's aerospace, automotive, the medical industry, consumer electronics, building construction. So the question is the plastic industry. Are you ready? Are you prepared for using 3D printing or additive manufacturing in your process? Another note is that petroleum feedstock is not the only feedstock available. Agri-based or even agro-waste feedstocks have made inroads based on lignocellulosic sources or monomers derived from the bio-based economy. So, for example, polylactic acid or PLA can now be derived from the bio-based feedstock. Polyesters, PET, in fact, are gaining ground in terms of raw material plastic sources for the industry. Now, when it comes to recycling, the easiest demonstration relating 3D printing and recycling is shown in this pictograph. So, for example, ABS, which stands for acrylonitrile butadiene styrene copolymer plastic, derived from the petroleum feedstock, ends up as an ABS molded interior car part that then goes into the assembly dashboard, let's say, of the car. The car is used for a certain miles. Eventually, car wreck or discarded, it will be disposed. If one can separate the plastic parts, those plastic parts can be recycled. So if you take this ABS, recycle it into pellets, one can either produce filaments or directly 3D print from pellets, which will be shown by our next speaker, perhaps later with the Ogberg machine and other types of 3D printing machines out there right now that uses pellets directly. So the recycled ABS ends up as a 3D printed part, as shown here. Once you have utilized the life of the 3D printed part, You can regrind it, produce pellets and filaments, and then the whole process is repeated. So this gives you a picture where recycling can come together with 3D printing. In the case of polyethylene, polypropylene, they can be recycled, but I can tell you from experience, they're very hard to 3D print. However, polyesters, PET, other types of plastics can in fact be segregated and recycled. They can be produced as filaments, or they can be directly from printed or blended with other types of virgin plastics to end up with the filament. So the filament industry is going to be a growing industry in the 3D printing field. Now, I used the term earlier, upcycling. Upcycling corresponds to the improved properties of polymer materials, or the use of polymer materials in high value added industries or additives. So, for example, discarded polymers can be recycled or upcycled into intermediates or chemical intermediates that can be used for personal care, cosmetics, lubricants as additives, or converted into other types of high performance plastics, thermosets, or thermoset elastomers such as vitrimers, which can be derived as polyurethane or polyester uh, type of products. Now, talking about the rubber industry, rubber again is a part of the polymer subgroup. Rubber is essentially based on thermoset elastomers or thermoplastic elastomers, natural rubber, synthetic rubber. The problem is rubber is hardly recycled. It's because of its thermosetting properties. However, rubber as today, majority is used as actually a heat source or fuel for the cement industry. So lots of rubbers are burned, incinerated, if you may, but largely the use of it for cement manufacturing. So recycling of rubber is possible, except that you need to find better ways or chemistries to utilize them as feedstock sources. Now, the way we've done it in terms of research, and this is really the emphasis on my research activities as a professor, is that we utilize nanomaterials or add nanomaterials to polymers or plastics, forming nanocomposites with the percolation theory, allowing us to find the high performance based on composition ratios. So we can use carbon nanotubes, graphene, nanoclay, nanocellulose. A good number of these are commercially available. The mechanism can be in terms of preventing stress crack propagation, or barrier properties or catalytic properties when blended with plastics. So a number of our research publications and activities are based on nanocomposite additives for plastics, for rubbers and thermosets. And we've used techniques like FDM, SLA, SLS, VSP, to work on a variety of nanocomposite projects. And we publish a number of papers. I'll be happy to correspond with anyone, or you can go to Google Scholar and look for the latest of our publications in nanocomposites and 3D printing. So several stories here based on research that I did with some visiting scholars from the Philippines. So for example, nanocellulose, which is derived from abaca or coconut, can be derived by breaking down the cell wall, lignocellulosic sources or fibers, which can in turn be broken down into elementary fibril and then eventually the nanocellulose material. So specific plant sources have a variety of nanocellulose structures. In the case of abaca and coconut coir, we can derive nanowhiskers, as shown here, with a high aspect ratio as observed by transmission electron microscopy or AFM. So this nanocellulose, we can mix it with the resin used for 3D printing in ratios from 0.1 to 5%. So when we mix CNC with PEGDA, you can see that this material can then be used for VAT SLA photopolymerization to produce parts. So by way of this movie, this is a Formlabs printer where we added the nanocellulose with the PEGDA resin or a formulated resin, and then 3D printed the object by photopolymerization, which you can show uh, building up here on the elevator stage. So we have measured properties, and indeed, even as little as 0.3 weight percent loading of the nanocellulose, we get a doubling of the tensile strength, the elongation at break, or the a dramatic increase in fracture energy. However, the tensile modulus is retained in a variety of compositions. So here you can see that the properties such as compression, flexural strength, tensile strength, elongation at break, or other thermomechanical properties can indeed be improved with 3D printing using nanocomposites. And here is a picture of the specimen. Perhaps this can be an artificial ear, a prosthesis device that can be used in the medical industry. Now, another story is the use of chitin. Now, chitin is derived from crustacean, shrimps, crab. We can isolate this by digestion, let's say using base, and then finally conversion to the amine containing chitosan polymer. So, as polysaccharides, this can be blended again with the resin. So, this is for you shrimp lovers or those who like to eat shrimp, which I do. You can recycle or reuse them. So in this case, the chitosan derivative is complex with the surfactant mixed with the resin, and then we can 3D print them, shown in these objects, with improvement on the tensile strength values, toughening as shown here compared to a native resin with as much as 8% addition of the complex chitosan. And here are the prints, a gyroid structure, a bolt, and this was produced again by SLA, so we can get very high resolution in their swelling behavior. Now, let me finish this segment in terms of summarizing my Philippine engagement. So for many years, I've been involved with working with companies, universities, and the Department of Science and Technology in carrying out applied science or training PhDs. And we emphasize now Industry 4.0 is the role of digital manufacturing or 3D printing is going to shine where we need high value added products and manufacturing processes. Because of our global relationships, manufacturing done in the Philippines can impact manufacturing in the US or in Japan or other parts of Asia. So what we need to capitalize is on our human resource, our technical resource, bringing the best of technology as fast as we can to adapt into this globalized manufacturing environment. So communities fostered by networking or building up, let's say, your association to spread the knowledge to your industry is very important, and therefore this conference is an example of how you build this relationship. I am for encouraging careers in the science and engineering field. Obviously, as a professor, one of my joys and roles is, of course, to train young minds and young careers. We do a lot of research where we translate the best of the basic research platform into the market, and we do this by translational research or applied research. And therefore, the success of our customer, quote unquote, or our client is our success as well. And in the Philippines, I engage in mentoring, but as well as consulting with a number of companies such as San Miguel, Chemres, EDC through the years. So, for example, in my lab, and this was a picture taken with some of my PhD students at the University of Houston then, I've trained a lot of Filipinos to get their PhD degrees with me. Some of them have gone back, but a good number of them have stayed and have been part of the industry here in the US as well as in the Philippines. And my recent lab here at the University of Tennessee, we do a lot of mentoring. This is a 3D printing portion of my lab, and we're open for business and collaboration. In fact, the Department of Science and Technology, a long-term collaborator, which can be explained by Engineer Lisa, is part of that collaboration ecosystem. So going back to 2015, we initiated a program with the DOST. We shared on training a number of Filipino visiting scholars. This was done at Case Western Reserve University, where I trained them in the area of additive manufacturing and materials research. And through the years, we have engaged also with bringing students to the Philippines. This is the case where I brought a number of teams, and I'm an advisor of the group called Engineer Without Borders USA, where we did outreach to various high schools and universities in the aspect of 3D printing, as well as social projects that help communities to bridge the gap in technology, knowledge, and problem solving. So as I mentioned, and you can actually go to AMCEN Philippines. This is realized. This I like this picture because of the blue background, but otherwise, AMCEN Center exists, and you can visit them right now. Will have a chance to visit the latest and best of the 3D printing equipment, and it's open for business. They do a lot of collaboration, training, conferences, but more importantly, projects, as you'll see later, let's say with the plastic industry, the defense industries, and other types of manufacturing environments. So I played a large role together with Engineer Lisa and Dr. Basilia in setting up the framework, but the Secretary of DOST and the Undersecretary, Secretary De La Peña, and Undersecretary Guevara were the proponents, if not the big supporters of this center. And you can learn more about that during the Q&A. But suffice it to say, this is a unique center because of the collaboration on the material side, development with MatDev, and the engagement with industry with Rapid AdMetech led by Engineer Lisa. So this is a unique center because in one center you can address the challenges of materials development, testing, as well as its incorporation or evaluation in the 3D printing manufacturing environment. And they have a lot of metrology tools, combination with other types of formative manufacturing, including injection molding, thermoforming. So this is really a one-stop shop, if you may, in terms of possible engagement with industry. They have been very active, especially with the start of the pandemic. One of the things that 3D printing demonstrated its prowess and capability is the rapid production and prototyping of PPEs, and let's say engagement in research such as the development of the ventilator. So you can clearly see here that 3D printing can be deployed in emergency cases as well to adapt to the needs of the times. Now, Philippine industry can engage a lot with the additive manufacturing sector, both on the low to medium, as well as the high technology industries. To bridge this gap, one has to find a good entry point for additive manufacturing in terms of the business model or the ROI. And I dare to say that the best investment you can make right now is to explore the area of molding, tooling, jigs for the industry. And you can focus this, of course, together with production, but it's used in the production of tools to support your industry. The reason is tools and molds are one of the biggest expenses of the plastic industry. Imagine if you can save as much as 70% in both cost and time for tooling and molding. That is the value proposition. So in molding and tooling, then you can emphasize on combining, let's say, machining together with 3D printing to produce the right mold, which can be used for prototyping the mold or production of your limited number of pieces, or for studying the design of the final mold, which can be translated to an actual environmental mold. So the disadvantage and advantage can be studied. Again, where 3D printing shines, the 3D printing manufacturing itself is when you require high complexity or the combination of parts. So just being able to combine 10 parts and reduce it to 3 parts is already a very good business model. And 3D printing shines very much in this type of projects. On the other hand, again, complexity is an advantage with 3D printing, but a disadvantage is, of course, the high cost of manufacturing if you're thinking of manufacturing a million pieces. But if you focus on the mold or the tool itself, then you unlock the value chain. So in making the molds, one can use prototypes based on thermosets, thermoplastics. So for example, using the SafeCAD design, yeah, you can use indirect tooling or direct tooling to produce the mold. Combination of milling, machining produces a very polished part. There are machines that combine both. And here you can see in the automotive industry, the molds, the tooling is very important. Some of this costs in the hundreds of thousands of dollars to produce. Delays of 3, 6 months can happen. They have to be shipped, and therefore you have to pay for the cost of shipping. So imagine if you can produce this locally, or you can produce the molds in-house, where you can utilize them directly for production. This has been demonstrated in many ways. And in fact, this is the focus of Oak Ridge National Lab, where in addition to the 3D manufacturing demonstration lab, we actually have a big operation on injection molding, thermoforming, together with the 3D printing lab. And if you have an opportunity to visit Oak Ridge or my lab, I can give you a tour on this facility. It's called the Manufacturing Demonstration Facility. Fortunately, before the COVID, the DOST group that trained with me, including Engineer Lisa, had a chance to see the demonstration facility. In fact, I dare to say that AMSEN was modeled after Oak Ridge National Lab in terms of operation. So you can have a glimpse of how this can be translated to the industry. For example, the big area additive machine, which is not available in the Philippines yet, can 3D print very, very big parts, including uh, uh, parts of aircraft or boat or automotive um, part. This has been demonstrated, let's say, with using PLA or ABS or PPS plastics. So, for example, this is a 3D printed Jeep, a wheelless Jeep out of the World War II design. Obviously, this is not produced now, but it can be 3D printed. Not all of these parts were 3D printed, but you can actually view this Jeep in a museum. For sure, the rubber and the glass parts were not 3D printed, but I would say about 70% of what you see here was based on 3D printing. So you can see here, additive manufacturing will impact many sectors in the industry, including the future in automotive assembly, electronics, or packaging for electronic products, plastics and parts production. Parts replacement is a big deal. Agricultural equipment repair, defense procurement, and so on. In fact, I would want to see distributed healthcare as one of the benefits of 3D printing in the Philippines, where prosthesis or orthesis devices can be made readily available to address personal medicine or accessible medicine. So again, you can see here high value adding in terms of tooling, parts replacement, defense procurement will happen. And in summary, I've shown you the importance of 3D printing and materials development. Although plastics is a big problem, there is a big potential, especially when the circular economy is realized. Plastics refer both to thermoplastics, but polymers is a bigger term which encompasses rubber and thermosets. So you should look at those parts of the industry as well. And I did not talk about metals and ceramics, but that's another technology or value chain for 3D printing. The time to invest is now if you want to be at the forefront of this technology and its growing adaptation in the industry, linking up with investments, let's say with the government and other private sectors. So right now, the Philippine government invested a lot in this center. So I hope you take advantage of it. We designed it as such. I believe Engineer Lisa will also be at the audience to answer any questions, but I'll be happy to answer any questions. And thank you very much for this time as well.
All right. Thank you, Dr. Advincula. I will end your screen sharing and also just jump out and open the room, the floor for the Q&A for everyone. Delegates, if you feel free, say yes and say good thank you to Advincula and especially raise your questions right now. Now the floor is open. Let's go to the Q&A mode. If you, Dr. Advincula, are you still awake? Okay,
Yes, yes.
several questions to answer, maybe. Okay,
Okay.
so we have several questions under the Q&A mode right now. You can pick one and publish them. Let's discuss that.
Hmm. All right. So, one question is, how does production look different when additive manufacturing is the process? So, I can outline the steps. First of all, additive manufacturing can be used for prototyping. As I distinguish, there are three types of manufacturing: formative manufacturing, subtractive manufacturing, and additive manufacturing. So what you do with molding, casting is a type of formative manufacturing. When you do milling, net shaping, that's a type of subtractive manufacturing. So additive manufacturing is an option. So obviously, one can use the same CAD design for subtractive manufacturing, and therefore you have these three options. So again, additive manufacturing can be easily used for rapid prototyping, but also for production. So you can actually produce the part or produce the tool using 3D printing.
Fun, fantastic. Let's go to the next one.
Okay, next one. All right. When working within a global supply chain, product and market complexity is the real challenge. Okay. Do you think additive manufacturing can really change the way products are realized? Thank you. Yes, I'm a believer in this, but I have seen it. And back in 2015, when I started working on additive manufacturing, already there are many companies that are proponents of bringing this rapidly into the market. And there are many machines, as you already know, but use of high volume production machines is still out there. One can go to, let's say, massive printing or farming to compete with the high volume, low cost formative manufacturing. But then I would say a big advantage of additive manufacturing is materials. You have so much material choices, and one can easily go from thermoplastics and see the value chain in thermosets or elastomers. So as I said, polymer is a big term, and plastics is just one. And when you look at the ability to, yes, for example, use thermoplastic elastomers. So polyurethane is a plastic, but it's also a rubber. That might demystify things because when you have parts that need to be very flexible, you obviously need certain type of plastic properties, and thermoplastic elastomers fit the bill. So I would say the complexity of the manufacturing process will necessitate new materials and new manufacturing methods.
Yes, that sounds a great and big and potential market. Let's go to the next one, and next one will be our last question.
Okay. In your opinion, what can business leaders do to make better decisions in order for them to react to changes in materials, customization, continuous improvement, etc.? Okay, I do work with a number of companies. I do consult with a number of companies that ask me these questions too. Of course, the bottom line is the bottom line, the ROI. Okay, how much return on investment you can make, how long, and why do you want to invest? So you have short-term and long-term goals. I can tell you that even for short-term goals, 3D printing already makes a difference. Now, you don't have to invest on the equipment per se, but you can invest on access to the equipment. So, for example, AMSEN was designed to be a center that is available for use by the industry, both for rapid production, rapid prototyping, rapid production, but also for materials development. As I said earlier, you cannot distinguish the materials aspect with the manufacturing aspect because they go hand in hand. Materials testing meaning you may have a choice of commercial materials, but then you have to test their performance before or after manufacturing. So I would say that to make a good business decision, you need to consider these factors. It's not necessary that you have a big capital deployment, but access to the best technology is very important. The investment ROI is both a short-term and long-term decision-making process. Right now, I see numbers, or rather, I hear numbers that go between 10 to 70% in terms of cost savings and time savings when you adapt 3D printing in your tooling or molding process. Essentially, if you want to be very nimble in adapting to your customer or designing for your customer, you will not wait for months to get your mold, but rather you will probably get your mold in 3 days by
Yes.
employing 3D printing. So you need to realize this, and one should not be afraid to get into this decision venture making process.
That's very great. And before that, I would like to thank you once again, Dr. Advincula, for taking the time, despite the time difference, to be with us today live. We're truly humble by this. We hope that can grace our event. We hope you can grace our event next year. Please take care. I know it's really late at your time. Thank you, and have a good night.
Thank you, and you can contact me by email, radvincula at gmail.com, or of course you can search for me at the website.
Would
And
you like to also share by typing your email, contact email in the chat box for delegates too?
yeah, let's do that. RCA41 at case.edu, and you can, again, if you forget this, you can Google my name and the university. Probably you'll see something that looks like me out there, but you can
Thank you.
contact me.
That's wonderful, Dr. Advincula. Thank you for your time today, and looking forward to see you attending our future events too.
Okay, thank you, Jack, and
Okay.
have a good conference.
Thank you. See you. Thank you, Dr. Advincula. That's very great. Once again, thank you for gracing our event. The honor is ours. Our next speaker is Miss Lin Wei Yan. Lin Wei Yan is the manager for additive manufacturing of ABRG. She'll share with us the vast variety of materials for extrusion-based additive manufacturing. Let's all welcome Miss Wei Yan. Wei Yan, you have the floor now.
Good afternoon. Welcome to my presentation, and I want to introduce you to our basic concept of the machine and what it means by vast variety of materials that are readily available for production in our freeformer. Hello, my name is Lim Wei Yan. I started in ABRG in 2015 in the application team and is responsible for sales and application support for the Asia Pacific region. This is my agenda that I have today. I will start off with process principle with a short video and what kind of materials have we already successfully tested, as well as some case studies by our customers. Some of you may or may not know ABRG. I will just give you a brief introduction. We are a machine manufacturer for almost 100 years now, and our main business is injection molding. In year 2013, we first introduced our 3D printing solutions for the market. The idea was that our injection molding customers should have a tool to do functional prototyping and also small series production with the same material that they use in injection molding. So yes, we print with granulates, standard raw material, and we have an open system so our customers can use the same raw material as they use in injection molding. To summarize the whole workflow of the freeformer, this is a short video. If the video appears laggy due to my internet connection, you can visit the ABRG official YouTube channel for reference. So thank you for your attention. The short video actually illustrates most of our process and what we can do. So to further explain, the plastic free-forming, which is a method used here, is actually an extrusion-based manufacturing technology. In the material preparation unit, the pellets or the granulates are plasticized with a 15 millimeters rotating screw in a heated barrel, just like injection molding. The plastic melt is then pushed towards the nozzle and is discharged as a string of droplets by opening and closing the nozzle. The melt material, which is necessary to discharge the droplets, is generated with a forward movement of the plasticizing screw over here, and the precise reproducible discharge is enabled by a non-return valve that closes the screw as the screw advances. The non-return valve is actually located at the front of the tip of the screw over here. So the nozzle is closed by an expansion of the piezo actuator located in the top area of the discharge unit, and when the nozzle is opened by the mass pressure, the material flows through a 10 micron gate at the tip of the nozzle. So this is actually the piezo actuator here. So when the melt material pushes forward, the mass pressure actually pushes the needle up, touches the piezo actuator, and the material comes out from there. The droplet discharge is then synchronized according to the movement of the build platform, resulting in discharge frequencies of up to 300 droplets per second. And typically, the layer thickness that we are able to reach are in the range between 100 microns and 300 microns. So let me go a little bit deeper into materials and properties. So the most interesting feature of the ASEAN plastic free-forming system is that the nozzle closure system, which makes it possible to handle thermoplastics material with a very different properties. The process even works with materials that has very low viscosity, and as long as the melt pressure is high enough to open the nozzle. In order to obtain the best part qualities, we need to take into account the different material properties, especially the viscosity and temperatures. This will lead to varying shape and size of the droplet as displayed in the bottom right corner here. As you can see, the droplets here are a little bit shorter and these are a little bit longer. So these are actually results from different viscosity and temperatures. The data processing software allows the user to adapt the different parameters of the new materials that needs to be qualified. The same applies to the ability to vary the density of the part, as you can see here. We can also place droplets closer together to create a very high density part, which gives us a very high mechanical strength in return. In this example, is a PC cube polished on all sides to show not only the clarity, but especially the density of the part. Vice versa, we are able to space out the droplets and hence reducing the density of the part. In this example on the right, it's actually a TPE printed with less density that mimics the function of a sponge or filter. The mechanical properties that can be reached are very comparable to injection molded parts. We did a study with printing some tensile bars to show how close the mechanical properties really are. The black bar here shows the properties based on polycarbonate. The dark green here shows strength that is printed in the flat direction horizontal, which is in XY, and the light green here shows the tensile bar printing upwards, which is in the Z direction. Generally, the Z direction is always weaker due to the process of 3D printing. That's where the layers are stacking on top of each other. Results can vary with different materials, but this result shown here based on polycarbonate PC, and we can see that the results are generally very close to injection molding. We are reaching about 99 to 100% in both directions. The unique combination of processing pellets with this droplet discharge and the nozzle closure system allows us to cover a wide range of material properties. Amorphous plastics such as polycarbonates, polymers are widely used already in AM industry because of their low shrinkage properties. However, for some semi-crystallines like polypropylene we have shown that we were able to achieve good mechanical and functional properties. The unique properties of PP opens up applications that has living hinges and snap fit functions. We also have success in printing thermoplastic elastomers like TPUs, TPEs, and SEBS from Shaw A harnesses as low as 20. I state the lowest possible because the softer the material is, the harder it is to process. We see here a very special range of materials which are in medical and biodegradable polymers like the polylactides and polycaprolactones, which are used in printing patient-specific implants and printing of controlled drug release applications. These materials are normally already gained FDA certification by the material manufacturers. So the certification is not done by ASEAN, but by the material manufacturers. That we have some, and then we have some special materials that we have successfully processed with the freeformer. This includes special compounds with conductive or flame retardant additives. In order to work with a wide range of materials, we do have partners to work with us for creating different kind of support materials. So in the middle, bottom middle icon here, you can see that we have 3 different types of support materials, and these materials are meant to work between the amorphous materials and the semi-crystalline materials. As mentioned previously, that one of the, As mentioned previously, that we have a wide range of materials that we have track printing. So one of the highlights at our booth this year at Formnext is printing of cranial implants. This implant is printed with a high performance peak. To be precise, we are using the material by Evonik called VestaKeep. This application shows the high potential of the latest achievement in further developing and adapting our AM technology for high performance materials. The Freeformer 300 3X can be equipped with a water heat exchanger, which allows us to reach a build temperature of 200 degrees, a build chamber temperature of 200 degrees Celsius, and a melt temperature of 450 degrees Celsius at nozzle. This is normally required to process high performance materials. For instance, the Oton PEI is also an interesting material that is also presented at the exhibition. As mentioned previously, that one of the unique strengths of the freeformer is printing in soft materials. Because we can directly use the original material, which is a granulated form, they are also used in injection molding. For example, we were able to present TPs and TPUs which are medically certified with skin contact or blood contact applications. These kind of flexible materials can also be used in the automotive industry, in applications such as ceilings, bellows, weather scraping for car doors, or car door joints. Of course, not printing the whole joint, but the connecting part of the car door joint. We already have several automotive companies and suppliers working with the freeformer system, covering a wide range of soft applications. Printed TPUs are tear-proof for functional use, as you can see in the GIF here. Behavior of printed TPUs and TPEs are very, very comparable to properties to injection molding. It is not unusual. It is now I would like to present an application with a 2-component part that demonstrates the great value that we can obtain by combining 2 materials. In this case, a hard-soft combination. This is a special gripper. This is a special gripper that you see in the middle. This is used in actually the medical industry, and this actually has 2 materials, actually 3. Right in the middle, where you see that it's hollow here, it has supports material filled in, and in the hard portion, it's actually medical approved ABS. On the outer part, which is a soft TPE that's medical approved as well. This is actually a function to grip like medical products in a clean room automation production line. So for hard-soft combination, we are able to print housings as well, hard-soft housings, like this over here, all right, and spring elements that are used in actually cycling. So as you can see here, printing with two materials opens up the possibility for further design capabilities, and that does not restrict the users of thinking additive. So as you can see here, this is also a two-component part that demonstrates a great value that we can obtain by combining two materials, in this case, a hard soft material. This is a special gripper for removing a handle. These green handles are used in actually the ASEAN dryers. They are called the thermal leaves. These dryers are manufactured by ASEAN. So a lot of parts are directly manufactured at our factory in the Black Forest in Losberg. So these handles are produced in actually our facilities in our customer center. One option that you have when planning such productions, right, with these parts is that they fall out from the mold into a catch pan. But in a sense, when it drops into a catch pan, there will be optical damage to the surfaces and probably dents and all at corners. So to prevent this, we actually need to redesign a customized gripper for a robotic system so that this part can move gently from the mold, right? So designing this part also gives us the possibility to present these two material printing. So the second advantage that we get from such an approach is that we can automate the process without the need to remove the spool. So the spool is normally the plastic residue from injection molding. So the traditional gripper was not suitable in this case because of the limited space between the mold openings and the position and orientation of the part in the mold. So this is the reason why we had to develop an alternative. So it is not unusual to design a gripper in additive manufacturing, but many manufacturers already do this and employ different AM technology for this application. But this special feature of our customized gripper is having a hard actually polyamide housing over here and a soft TPU membrane over here. So when the air passes through the air duct, it actually blows up over here. So it grips the handle with actually no scratches or no pressure at all. It's like a foam closure or foam closure mechanism. So the function of the gripper is enabled by compressed air again, and this actually retains the hard housing of the polyamide actually retains the shape of the soft TPU membrane, which is really thin, about I would say 0.6 millimeters. So by this way, we were able to remove the handle from the mold gently without damaging the surface, and something which is hard to achieve with traditional grippers and or from other AM technologies. Especially for this case, the TPU membrane have to have enough air tightness for the proper function of the gripper. So in the next slides, I would like to present two case studies from our freeformer customers, which have been using the freeformer technology for a couple of years now, and they have been using or implementing the AM technology right into their factory space successfully. One of them is a company name called Mosca. Mosca have installed over 100,000 strapping machines worldwide. And they are one of the largest common suppliers for strapping and securing systems. The challenge for Mosca faces its high amount of spare parts that needs to be supplied quickly to the customers worldwide. Some of these spare parts are very difficult to reproduce using traditional methods. So this includes actually reprogramming their CNC machines and capacities, which makes them unavailable for other functions. And that's the reason why Mosca decided to go into additive manufacturing. So the most important requirement for the freeformer for Mosca's requirement is actually the strength, the dimensional stability, and production time. The parts you see here in the picture are produced with an amorphous polyamide material that meets all requirements in mechanical properties. So in this, Mosca has decided to go on further with the freeformer and have identified more than 100 series of spare parts that can be produced additively using the freeformer. Another important aspect here is the cost of the low volume production of these parts. We are speaking about 1 to 50 parts per year for each design. So the strap guide, for example, can be manufactured in about 80 minutes, and the cost of the part is reduced by at least 75%. So in the end, bypassing conventional manufacturing methods and eliminating the need of outsourcing enables Mosca to produce these parts at a fraction of its previous cost. So the next case study is from our customers called Summer Plus. Summer Plus is actually a medical device manufacturer based out in Switzerland. And they uses injection molding to produce medical components and implants. So Summer Plus already has a very broad experience in AM, but none of these machines were capable so far to produce biocompatible materials. So the biocompatible materials that Summer Plus has been using for injection molding. So they want to use the same material from injection molding also in 3D printing. So this is where the freeformer come in place. So first, Summer Plus uses the freeformer to speed up production product development. In the picture you can see here, it's a replacement for a meniscus component which was 3D printed by the freeformer in two different materials, and this material is actually polyurethane. So the customer of Summer Plus. So Summer Plus is a manufacturer, so they have they supply such implants for customers. So one of the customers has like the possibility to test this product straight away, just a few days after development phase started. So the moment the design is out, they started to print, and this allows the customer to test this part immediately. So not waiting, there's no need to wait for an appropriate mold for the first parts. And this means the product development life cycle is reduced by 75%. And the next step is definitely directly printing such customized implants with the use of medical FDA approved materials. Another project that involves Summer Plus is actually to test the capability of bioresorbable polymers together with Evonik. So Evonik is actually the provider of the materials such as polylactic acids, the polycaprolactone, and the polyurethanes. So this resomer material from Evonik is a special PLLA material that contains 30% ceramic additives, which helps in bone healing, which promotes bone healing. Sorry. And as you can see from the picture, these materials are used to print actually fracture plates and scaffolds. So I've come to the end of the presentation, and in summary, our plastic free-forming technology is a flexible technology providing an open system that allows the user to choose from a large variety of already qualified materials. However, the customers are not restricted by just qualified materials. They are able to qualify their own materials as well. I have presented two case studies which demonstrated the capabilities of our AM technology and showed that our system is ideal for functional prototyping and low volume production with many original injection molding grade material. If you're interested in the shared case studies or others, please get in touch with us to get a detailed copy of the case study done together with the customers. I hope you enjoyed the presentation, and I think we still have some time for questions. And that's the end of my presentation.
That's really interesting. I love the video the most. Yeah. And I'm glad to see that actually in the chat box during your presentation, there are many discussion and also many questions raised up for you, Lin Weiyan. So are you ready to read those questions really quickly? Maybe give a link and let's check if we can answer them.
Sure. All right.
Okay,
So,
even we transform the platform. Delegates, can you still hear our voice from Lin Weiyan and also from my voice, Jack? If you can hear us, say yes, clear. in the chat box. Thank you. And Wei Yan, please read this question and start answering.
All right. What is the tolerance of the parts printed as well as the minimum thickness allowed? So I choose this question because I can answer the first two together with this. So the tolerance of the parts, right, are typically between 0 plus minus 0.1 millimeters to 0.15 millimeters. So depending on how long the part stays in the chamber, in the heater chamber, and sorry, you clear off the. So what is the minimum
Sorry, let me
thickness?
give you back. Yeah.
Sorry. Yeah. So what is the minimum thickness? Or I will expect that the customer is asking for like wall thickness. So the minimum wall thickness is actually 0.6 millimeters. So how do we derive 0.6? Is because we use a 0.2 nozzle size, and the droplet size that we produce is about 0.2 millimeters as well. So using this, wall thickness needs to have at least 3 droplets to form a wall. So 0.2 millimeters multiplied by 3, that will be the minimum wall thickness. Yeah.
Okay,
so,
that's all. I believe
yeah,
there's
so-
another question about the size of the nozzle too, right?
Yep, the size of nozzle is 0.2 millimeters, producing 0.2 millimeters droplets. That's
You're
what I
answering this
mentioned.
question already?
Yeah, yep.
You have to
Yes.
publish first, otherwise the others will
No,
not see it.
yeah, because with this question, it actually covers that as well.
Ah, okay, included.
Yeah, that's
Great.
why.
Okay.
Yeah.
Okay, next one, please.
So hang on, I'm having trouble scrolling. Okay. Considering the same materials and the same part, how do you compare the thermomechanical properties of similar part done on additive method on Arbok printer versus that of the same part done with conventional injection molding? So basically, we print the same tensile bars with the same DIN ISO standards. So every material in injection molding has actually a technical data sheet. So we print the same size of a tensile bar. We do the same testings as of how they do it in injection molding, and we compare it. So in the mechanical strength graph you see, right, that's the reason why we have 2 different directions, X, Y, and separately from Z, because 2 different directions, 2 different strength.
Is that ambulance from your side?
Yeah, COVID is not really doing very well in Singapore. That's like ambulance
to
going
say.
every day everywhere. Sorry.
Yeah, it's okay. Yeah, it's good after your presentation. Okay, let's
Yeah,
do the
yeah,
next
yeah.
one.
Okay, so let's choose the scroll. It's not working very well for me. Sorry. Okay, so is the freeformer able to use fiber reinforced materials? So as mentioned, actually in the video, that our melt material flows through a 10 micron gate at the tip of the nozzle. So by having that, we were not able to use big fibers or long fibers in the process. So we are able to use any kind of additives or fibers or reinforced ceramics like the Evonik material, but these particle size are all less than 10 microns. So it flows through the gate nicely.
Okay, that's all.
Yeah.
Okay, so
yes.
delegates, before you go to the next one, I believe that next one might be our last question. And before we go to that, delegates, according to Lin Wei Yan, maybe yes, they would like to share the playback video after this live presentation today. So you have the chance to replay or to catch up some parts you've missed in the previous presentation. And also, maybe you could share this great presentation and videos with the others too, right? So Lin Wei Yan, is that okay? We will do that after that. So make sure
Yes.
you fill in our feedback form, and we will send you the playback link and also the other feedback content. Okay, too. Lin Wei Yan, let's go to the next one.
Next question, is it? Okay.
Do we have any?
We do. There's something on the print speed. Yes. So typically the printer prints on what is the print speed, right? So typically the print speed is about 2 to 14 cubic centimeters per hour. So why is there a range? Because when we print the inner filling area, we print it faster. When we print the contour, which is the parameter of the part, we print it slower to achieve a good surface quality. I hope that answers the questions.
Okay. So that will go to our end of your presentation session.
Thank you
Please
very much.
make a conclusion and also saying goodbye to the delegates too.
Thank you very much, everybody, for your attention. I think Ronald wants me to get in contact. Arbor is all over in ASEAN region, so get in contact with any Arbor office, and you can get in contact with me. And thank you very much again, and stay safe.
Yeah, for
Yeah.
delegates, I know some of delegates leaving your contact information here already. You can email Hazel as our project leader, and also leave your contact information, contact email too, if you want Lin Wei to contact you later.
I
Or
actually left
just
my email behind as well.
yes,
So in
or
the group
just
chat, yeah.
directly email your further discussion or
Yeah.
questions to Lin Wei. Yes. Okay. Looking forward to see you in our future
Yes.
events. Okay.
Yep. Thank
So
you.
see ya. Bye bye. Stay safe.
Bye.
All right. That's from our presentation from Albert Lin Wei. So um, delegates, seize your chance to contact him. I mean, contact Albert, contact Miss Lin Wei for your further questions, further discussion too. So very good and detailed presentation, I have to say. Thank you. I never realized how deep and intricate 3D printing can be, delegates, right? I believe you feel the same too. Our last speaker for today, let's go to his slide. Okay, last speaker will talk about the two important topics too. First, how new hybrid solutions can combine AM with regular manufacturing methods. Second, how additive manufacturing can potentially extend a product's life. These are important aspects to know, so manufacturers can sustainably cut on production cost and improve manufacturing quality at the same time. Mr. Jonathan Ko, Sales and Marketing Manager of Manly Plastics in the Philippines, will tell us how. Let's welcome Mr. Jonathan Ko. Jonathan Ko, ready? You have the floor now.
Good afternoon, everyone. My name is Jonathan Ko. On behalf of our family, our entire 1,500 strong workforce, I want to thank you for giving us this opportunity to speak to you this afternoon. Our family has been in the mold making and plastic manufacturing business for over 5 decades now. I am part of the third generation of stewards of this business that was started in one small shop house in Manila's Chinatown in 1964. We have come a long way since then, and we hope to continue to grow by continuously providing value to the market. One of the technologies we have been pursuing and studying with great interest is additive manufacturing. I was given a topic title of what the organizers would like for me to talk about, and it is the following: how new hybrid solutions can combine additive manufacturing with regular manufacturing methods, and the possibility of additive manufacturing to extend a product's lifetime. So, to begin, what I would like to do first is to give you an introduction to our company, who we are and what we do. And I've decided to put together a video because I just think it's better than you listening to me for the whole 20 minutes or so of my talk. But before I show the video, I would like to apologize in advance because we really did not have a lot of time to put this presentation together. I only received the invitation last week, and so my team and I have had to scramble because, as you know, it is the holiday season and things are quite thankfully picking up here in the Philippines. And so we didn't have time to get a proper voice talent, and we had to resort to artificially generated voiceover. And I just wanted to say that up front, just so it doesn't get all weird when you start hearing a robotic voice midway through the presentation. There's also some pacing issues because of the time constraint. So if you would like a copy of the company introduction, you can scan this QR code to take you to the link of the video's location. So with that out of the way, please watch our company video and I will see you on the other side.
Who we are: product design house, mold maker, plastic product manufacturer, sales and marketing company. Product design house. We provide our plastic design skills to produce industrial and consumer products, turning your ideas into innovation. Mold maker. Techniques earned in our decades of existence in tool making, such as hand molding, computer industrial technology to design, create repair molds and models for mass production. Plastic product manufacturer. We supply and manufacture plastic parts to companies ranging from automotive, motorcycle, household appliances, consumer electronics, pharmaceutical, food handling, food packaging and food production.
So, given our background, the application of additive manufacturing technology in whatever form will seek to enhance our current core competencies. Additive manufacturing for us represents both a threat and an opportunity to our business. It is a threat because this technology opens up new opportunities for new players who have fresh capital, fresh ideas, and fresh leadership, not to mention thinking out of the box to potentially offer superior value in providing what the clients need which at the end of the day is functional or are functional and consistent quality plastic parts. Most customers, frankly, do not care about how things are made. They care about the product that is being delivered. We are in the mass production business after all, and being in this kind of business requires us to be predictable and consistent with products that we are delivering. As long as we meet the quality and price targets, things are generally fine. I believe the case is pretty similar with many manufacturers engaged in the same business anywhere in the world. When we decide on a technology, when we assess technology, we look at it generally from two lenses. The first lens is the technical lens. Is this particular manufacturing technology able to provide consistent product? And the second lens we tend to use to assess the technology is the bottom line benefit. Are we able to lower our overall cost of production? Unfortunately, we do not have a final answer for you this afternoon. This talk is not about conclusions. This talk is about where we are on our journey. In answering the question how hybrid solutions of additive manufacturing with regular manufacturing methods, in this case mold making and injection molding, here are our thoughts based on our experience so far. The first application, and I don't think this is news to anybody, especially if you have been following the additive manufacturing industry and technology for any length of time, the first application of additive manufacturing is really in the product development stage, specifically the prototyping stage. Before additive manufacturing, the options you have for prototyping is more limited. You can do hand-fabricated prototypes, paper, fiberglass, clay, resin, etc. You can do machine prototypes on a CNC machine using wood, cast plastic boards, or cast resin boards. Or if you have the budget, you can do soft metal tooling and then put it in an injection machine and make finished functional parts. Each of these has its own pros and cons, but we don't have the time to discuss that. YouTube and Google are our best friends for these fabrication technologies, for the research. What I would like to talk about is how additive manufacturing has helped with this. And generally speaking, it has helped in the following ways. First, it has shortened our prototyping time. Okay, I think that requires very little explanation, but briefly, you design it in a computer, you load it to the program, and you pray that it doesn't, the filament doesn't break or you don't have a problem midway, or worse, at towards the end of the manufacturing process, and you have to start all over, right? And second, and I think more important, is that it has enabled us to produce close to injection molded parts in terms of functionality without the need for investing in soft tooling, soft metals, in particular aluminum molds, that you still need to machine. And really the savings there is, since the steel is softer than tool steel, your machining time is a lot shorter. But then it still requires a lot of cost. This information, I think, is nothing new. Many people do it. For us, this has already become, thankfully, a standard part of our product development process. The next, more challenging combination of additive manufacturing with regular manufacturing methods is this: combining 3D printed products called inserts into standard injection mold bases. This technology application obviously allows you to do short runs, but I personally believe the frontiers of this particular application is only starting to be explored, and it can only get better. I say get better in the sense that I think as more material options become available, and in my opinion, more crucial, as more people get to work with this particular application of additive manufacturing, we can develop techniques in prolonging the life of the inserts, because right now a lot of these inserts, they only last for a very short amount of time. Somewhere between, in some articles I've read, they say up to 100, 150 shots. And then the insert is basically destroyed. I'm not willing to give up on that just yet and take it as a matter of fact. Just yet. This is the plastics engineer in me talking. And of course, the holy grail of additive manufacturing, it is short of a Star Trek replicator. I don't know if the audience knows what that is, but in the old Star Trek series, the James Kirk, Jean-Luc Picard time, people would just say computer, coffee, black. And the saucer, the cup, and the coffee just appears in front of your eyes almost in real time. Obviously, we are very, very far from making that a reality. Currently, the commercial applications for manufacturing outside of the novelty products, the personalized figurines and such, outside of that, in industrial and commercial applications, the applications are limited to high value, low volume, custom applications. We are talking about specialized parts for the medical industry and, of course, the aerospace, and to a certain extent, the automotive industry. Specifically, right now, Formula One racing, additive manufacturing is being applied to what we generally call specialized or even exotic applications. So just like in other technologies, especially in the old technologies like composites and plastics, it starts out with those kinds of applications, high value, low volume, specialized applications, right? So I think additive manufacturing will follow the same path. So I think it is just a matter of time before it grows and there's more adoption. There are simply way too many people and companies working on this technology for it not to progress, in my opinion. In our company, we have a small team of 4 focusing on this technology. We are working with equipment suppliers, material suppliers, both locally and internationally. We are also working with the government, specifically the Department of Science and Technology. They recently opened the Additive Manufacturing Center, or AMCen. We are also working with the Department of Trade and Industry, specifically the Bureau of Product Standards, to adopt the ASTM and ISO standards for additive manufacturing to the Philippine national standard. With all that is happening, I am confident that as far as the technology is concerned, it will continue to improve, costs will continue to drop, and the industry players will continue to consolidate. This is no different from the plastic industry currently. Resin manufacturers, equipment manufacturers, they all follow the same path. There's an era of excitement and rapid growth and experimentation and hype, which is followed by industry consolidation, and it creates a whole new ecosystem as companies, as users, as customers adopt that technology. I believe the question for everyone watching is this: how do you, as an individual, and to you as a member of a corporation, benefit from all this movement in the additive manufacturing industry? To answer that, I want to start with this. Business exists for 3 reasons: make money, save money, and grow markets. That's the goal of every business, and the success largely to what activities, what projects are pursued, and how well they are executed. This is my call to action for all of you. Educate yourselves in this technology. This is the key, because ultimately, all solutions that we will be able to come up is hybrid, if you think about it, because it is a substitution play. Because the products it is replacing is just that. It's being replaced. It is a substitute. Plus, I think most, if not all of us here, have existing manufacturing operations. So all solutions we have to come up with all the applications of this technology we have to come up with is a hybrid because it has to, as much as possible, fit into our existing businesses. The first question is, how will it fit? Right? The first step to answering that is to educate, to experiment, to learn the nuances of this technology. If any of you watching here today is in a position to provide resources and support and to champion this, please do. You know, the machine manufacturers, the software providers, they will do what they do. But us, the individual, the project engineer, the project manager, the designer, we have been sent here by our organizations to learn about this technology and to figure out ways to apply it to generate greater value for our organization, whether it's your own company or the company that you work for. Again, you have to get yourselves educated. And thankfully, because of the internet, there is far more content that can be consumed available out there. We are quite fortunate here in the Philippines that the government has invested close to $10 million to create the Additive Manufacturing Center. May I just take the time to promote them because I'm one of their biggest supporters. For more information on them, please see the link here. The beauty of having government investment in such a center is that equipment is no longer the problem. The capital expense has been spent. The challenge now is to develop an ever-growing community of designers and technicians competent in designing products for additive manufacturing. Operating and servicing these various machines are also very, very important, meaning having a group of people that can operate and service the machines. The challenge now is developing a growing set of material engineers that can create the various recipes with its specific physical and functional properties so that they can be suitable alternatives to the products made using other manufacturing processes. In other words, all the equipment can be there, but if there is not enough knowledgeable people for using it, the industry will not grow. And that, ladies and gentlemen, I think is the problem facing us, at least here in the Philippines, as far as the additive manufacturing industry is concerned. That is where we are at, and that is, I would say, the next hurdle we have to clear is. Now, I've been asked to say a few words about the possibility of additive manufacturing extending product lifetime. Here are my thoughts on it. Product lifetime is more about the decisions made on a product management level, a product design level, and dare I say, top management level. I say this because the length of a product's lifetime or the length of its useful life is largely influenced by the design principles or the design intent. And this is decided at the beginning of the product. A lot of talk now is being a lot of discussion is happening in terms of like circular economy and how that can be good for the environment. A big part of that is design for recyclability, design for remanufacturing, design for repairability, right? Along those lines, additive manufacturing can play a role in extending product lifetime in the following ways. It provides an option for creating your own replacement parts. Another is it enables you to create accessories to improve the functionality of existing products or to repurpose existing products over and above the original intent of the particular product being discussed or being remanufactured or redesigned, right? Or the product that has come to its end, the end of its intended life. But again, I want to emphasize that additive manufacturing is simply one of the tools that enable people with, and this is crucial, the right mindset and the right design skills to realize their designs. In short, it lowers the barriers to entry for people with ideas to realize those ideas, to make their ideas tangible. Again, we need to be working towards developing the skill set and mindset of the people to be able to maximize this technology, because the technology by itself does not generate value, right? It is in the application of the technology to, as corny as it sounds, make the world just a little bit better that generates the value. In closing, and I realize I've gone slightly over time, I would like to say the following. In closing, I believe the additive manufacturing industry presents an opportunity that is similar in scale to the personal computer industry created in the 70s, the 80s, the 90s onwards. In this sense, before the personal computer, the benefits of high speed, high capacity computational work is centralized to universities and a few large businesses. With the advent and the adoption of the PC, it became widespread. And look how it changed our lives. Imagine manufacturing tangible products in a similar, decentralized manner. Is it really that far-fetched? I don't think so. A lot of you are probably watching this from a, a cell phone that has more computational power than the supercomputers of 20 or even 30 years ago, of definitely 30 years ago. But here's what I know. Without a growing community of learned people that are figuring out new applications for the technology, testing the limits of the technology, and even modifying the machines to overcome those limitations, we will not get there. Imagine if we here in Asia will be leaders in this exciting new industry. That is the nugget of thought I leave with you this afternoon. Again, my name is Jonathan Ko. Scan this QR code to add my contact details to your mobile phone. Scan this QR code to download our company brochure. Thank you for watching.
Mr. Jonathan Ko, actually, he made a great pre-recorded video tell us to share while he was prepared to do the live Q&A with us. Okay, he left a message with me and I'll just read that. Delegates apologize that Mr. Ko cannot at the last minute join the live Q&A as he has to attend another urgent matter in his office. So he can address your question later if you publish them. You can contact us through Hazel if you have further queries. Thank you for your understanding. That's from Mr. Jonathan Ko. And yes, and Yay Xuan Go, thank you for that. And I'll tell Jonathan that you also very happy for his sharing. I believe that we all do learn a lot from his presentation, especially, yeah, maybe not that corny, but yes, we will try our best to make our world better, a little bit better day by day. Anyway, so I will just let Hazel to also, because I know the QR code on the screen flash really fast, right? So if you want, also fill in your questions in our feedback form. We will transform your questions to Mr. Jonathan Ko. Or if you would like us to arrange a meeting after this event, you can tell us your request too. So, Mr. Jonathan, even you're not here listening anyway, I have to say thank you, Mr. Ko, for the interesting presentation. So, at the end, we skipped this Q&A, but yes, we hate to say, but we have to say goodbye. This conference has come to the end. I will share this on the screen right now while I do the closing. Okay. Now, delegates, on behalf of the Ringer Events organizing team, thank you to all our participants who join us in this interesting and refreshing virtual conference today. We hope that you gain new insights and met new connections here today. As I just said, maybe make some friends or meet some potential business partners. Before you leave, we are looking forward to reading your feedback and suggestions too, in order to make better events for our dear delegates. So please fill in the feedback form. You can find it on the green button on the screen right now, or I pin this address, the URL on top of the chat box. Please fill in that. Send in your opinions and suggestions. To our guest speakers and association supporters, we appreciate you spending time with us today and for the insightful presentations you have shared. Once again, thank you everyone for gracing our virtual conference. This is Jack from Ringer Event. We can't wait to welcome you back in our next Additive Manufacturing Summit next year. And we have many other kinds of virtual events, even hybrid event in the next coming year. So I won't say subscribe us, but follow our step. Please go to our event website. You can find more, explore more conference for you in the future. Take care, everyone. That's the end. Thank you. Thank you for that. Bye-bye.